Okay, off we go. So we're going to pick up where we left off last time. So we were about to start this example. This is another example of how to parameterize. Remember what that means is that we're going to create parameterizations, right? And here we're going to parameterize a curve. We saw a couple of methods last time for how to parameterize. Tools for your toolbox, don't forget that point, right? I mean, don't think of any of these methods as here's how you do them. These are tools in your toolbox. Pick the appropriate tool for the appropriate job, and it's good to have a bunch of different tools because every job is different. Okay, so here we go. We're going to think about a wheel like so, and it's rolling along the ground like that. And as it rolls to the right, the wheel goes like that. But of course, the wheel is also going to rotate as it moves. That's how wheels work. Right? And now imagine that there is a reflector, as a lot of bicycle wheels have. There's a reflector attached to the rim of the wheel. And now think about, as the wheel rolls, what is the path that reflector follows? And y'all may have seen something like this in the real world, at dusk or later. Bicycle riding underneath a street lamp, and you see that scallopy pattern. Does everybody know what I'm talking about? We're going to parameterize that curve. Real quick side note, don't try to write the equation of this curve. It's really, really hard. I'm not even sure how to do it, to be totally honest. So very inconvenient to find the equation of the curve. But parameterizing is going to be pretty straightforward. Okay, the big trick, and keep in mind, this is the point to this example is to illustrate a big tool. There's also going to be a bunch of details. Yeah, we'll talk through the details. Okay, fine. But the big trick, the big point, is how vector algebra can be really useful in a lot of circumstances. That's going to be the big takeaway here. Sometimes you can take a complicated thing and with vector algebra, rewrite it as a sum of simpler things. That's what's going to happen here. So this reflector, I'm going to call that point P, where the reflector is, at some moment. We're going to think of that as being the location of the axle that I'll call A, plus this vector right here that I'm going to call D. It's kind of like a spoke on the bicycle wheel, right? So axle plus spoke gives you where the reflector is. Is that cool? Everybody on board? Okay. Yeah. So D is a vector whose tail, D is a vector represented by this arrow. This arrow has its tail at the axle and has its head at the reflector. Yeah. Right. Yes.
So the vector A is from the origin to the axle.
Yeah, that's right. So there's this thing where we very commonly like to conflate points and their associated vectors. And it's just really, really convenient because otherwise you have to technically define a bunch of other things that are morally equivalent, and it's just fussiness, right? It doesn't really buy us anything. So yeah, totally. If you want to think of the axle as being this vector, it's fine. I think it's going to be easier in this case to think of it as being a point and to think of D as being a vector. And again, right tool for the right job. It's a good question. Anybody else? So again, this is going to be the big takeaway, writing things as sums of simpler things. It's going to turn out that the axle is going to be much easier to describe. It's going to turn out that this purple D vector is going to be pretty easy to describe. And then we add them, and it'll give us the answer to how this wacky curve works. The weird motion of this reflector is going to just fall in our laps. Thank you, vector algebra. Okay, so one step at a time. Before we get into the details, we do need to think about what our parameter is going to be. And remember, when you parameterize, you're writing position. Here's our point again. I'm going to write that position, P, as a function of some parameter. What parameter do we want to pick? This is, there's kind of an art to picking good parameters. You want it to be natural. You want it to kind of make sense. You also want it to be convenient to work with. Those sometimes are conflicting considerations, right? But all else being equal, those are the things it'd be nice to be able to do. In this case, here's the choice I'm going to make. The parameter, I'm going to choose, let me make a good choice of color. That angle that I'm calling T. I'm calling it T because, again, it's kind of a routine choice to use as a parameter. We use T as a routine choice of parameter because it stands for time, and we like to think about parameterizations being in terms of time. Here I am not thinking about T being time. It's just, that's an angle that I think is going to be a nice combination of natural and convenient. And forget about time. So here's where I think it's kind of natural. When we start, right, at the start, the angle between down and the direction of the reflector is 0. Right? So when at the starting moment, T is 0. How convenient. Right? That's nice. Here's the other thing I'll point out. As the wheel rolls, T increases. Right? You got to use your imagination. As this rolls along, this angle is going to kind of keep going clockwise. This T angle will increase. So this kind of behaves in a convenient way. It starts at 0 and increases. Side note, kind of just like time does. Right? So pretty reasonable choice. Now it's not the perfect choice, and we're going to see in a moment that there's a downside to this choice, and then again, it's, pros and cons and conflicting considerations. But that's what we're going to go with for the moment. Okay, so yeah, observation number 1. Thinking about the axle. The axle, of course, is going in a straight line like that. Notice the y-coordinate is constant. The y-coordinate of the axle is just the radius of the wheel, so boom, that's an easy one. The tricky bit is to figure out what is the x-coordinate, right? This x-coordinate of the axle, you might say it's this, I'm going to say distance. I'm going to abuse the term distance is an intrinsically positive thing. Technically, coordinates don't have to be positive. It is in this case, but it didn't have to be. Anyway, x is that distance in this case. Okay. How am I going to compute that distance based on that angle, accounting for the fact that the wheel is rolling as the thing is rotating? And here's a physical observation. By the way, sometimes we have to make physical appeals. Sometimes we have to, wait, how does the physical world work anyway? Right? And here's what I think is the relevant point. This that I'm trying to get my hands on here, that's the amount of road that has touched rubber. Claim the amount of road that has touched rubber is equal to the amount of rubber that has touched road. Now we just got to think about that physically, right? That, in some sense, that's what it means for the wheel not to be slipping. Everybody buy it? So this is a fabulous observation. We're looking for this x-coordinate of our axle. The x-coordinate is the amount of road. The amount of road is the amount of rubber. And the amount of rubber is an arc of a circle and high school geometry and all that. You all remember all the old high school geometry formulas. So that amount of rubber, a.k.a. the amount of road, a.k.a. the x-coordinate, radius times central angle. Boom, there's our axle. All right. So we're halfway there. We've got the formula for the axle. Well, let me do it like this. We got the formula for that axle. And now we're going to move on to figuring out the formula for the d vector. That's this vector right here. Looks like a harder problem, but here's a mistake that a lot of students fall victim to, and that is to think that that D vector behaves as follows. That it starts off down here like this, and that it goes like this, namely that not only does it kind of rotate, but it also moves. After all, look at the arrow, right? This arrow, as the wheel moves, that arrow is moving. Well, you have to remember, vectors and arrows are not quite the same thing. We use arrows as a clunky tool to describe vectors, but let's keep it very, very much in mind. Vectors have direction, vectors have magnitude. That's it. Direction and magnitude. Vectors do not have location. Looks like it does. There it is. Look, I can point to it. There it is. It's got a location, right? That's not a vector. That's an arrow we're using to represent the vector, right? Arrows have location because that's how ink works. Vectors do not have location. Does that make sense? Does everybody remember all this? Okay. Right. So I don't have to worry about how the location of the arrows is changed. The location is a distraction. I can draw those arrows anywhere. And here's a convenient way to draw that arrow. That vector, let's draw it with an arrow with the tail at the origin. Oh, handy. Let's see if I can zoom in well here. Yeah. So what's the formula for that? Well, this is nothing to it. Y'all remember your trig. We have this angle theta, and pretty straightforward to see that that's the formula for that vector. We've got a wheel of radius A. This is like practically straight up the definition of cosine and sine. So, boom. Everybody happy so far? Unfortunately, I've already decided that I need to write everything in terms of t, this angle. I got to be consistent, right? I need position in terms of a single parameter. So I have currently now got d written in terms of a different parameter. So I need to figure out how to get rid of theta and get t into this formula. And the observation to make, and this is another straightforward observation, you got to sort of think it through, keeping in mind that that's our angle t, keeping in mind that theta, it goes kind of this way. Notice that as t increases, theta decreases, right? So the sum is constant, and pick your favorite moment. We can pick where t equals 0, I suppose. When t is 0, theta is 3 pi over 2, and the sum never changes. So the sum is 3 pi over 2, or said differently, t, what I need, theta, what I need to plug in for. What I need to plug in for there, theta is 3 pi over 2 minus t. And then you use your angle addition formulas. Side note, I do require that students, if you don't already have them memorized, you do need to know the angle addition formulas that come up quite a bit. Many of y'all are engineers. You're going to need, the world is full of circles. That means that engineering is full of trig, and the angle addition formulas are going to come up, and I think everyone should know them. And likewise for this class, we're going to need those formulas. So make sure you know the angle addition formulas for sine and cosine. And you plug this formula for theta into there, angle addition formulas, and this is what you get. Details that y'all can check on that. Let's see. Oh, and I can go full screen. I always forget to do that. Okay, so all together then, let's see if we can, here we go. So all together, if I can fit it, the points that we're trying to describe, A plus D, well, we've already worked out that the axle is that formula. We just worked out that the D vector is that formula, and adding them gives the parameterization of the reflector. How we doing? So again, a lot of details. Don't get lost in the details, right? Details are important. You got to be able to get down and deal with the details, but you also need to be able to stand back, see the big picture. The big point here is that vector addition allowed us to turn something that we otherwise wouldn't know how to get our hands on and rewrite it as a sum of separate things that we can totally deal with. Right? Not that big a deal. Just details is the only problem. Okay, so vector addition for the win. Okay, moving along. Here's another example where we likewise are going to use vector addition. We're going to parameterize a line. Let's parameterize this line right here. If I'm going to parameterize a line, I need to be able to tell you which line I'm talking about. There's lots of lines. Right? Which line do I mean? I mean the line that goes through that point and that's parallel to that vector. And there's only one line that goes through that point and that's parallel to this vector. Is that cool? Okay, so given the R0, given the V, how am I going to describe this line? Well, I need to, if I say I want to parameterize, I need to describe points with a formula. I need to be able to generate points on the line with some expression that involves a parameter. And here's the easy observation. Easy observation is that, R0 is given. And then this vector here is clearly a multiple of this given vector, right? Because by assumption, this vector is parallel to the line. These are 2 points on the line. Their difference parallel to the line. So scalar multiple of that vector. And so green plus purple will always give me a point on the line, and I have a parameter. T is my parameter, so position is a function of one parameter. It's a nice little trick. Everybody see how that works? Cool. Again, vector addition. It's the thing that makes it work nicely. Okay. Moving along. Y'all remember we discussed last time this is going to happen sometimes. Again, there's too much. I can't do everything in class. There are these edge topics that I want to be able to help. I want to be able to give you something that I hope you'll find useful. We just can't do it in class. So I hope when you read this example, I hope you'll find that useful. I think this is a pretty readable example. Give that a look. I think you'll find it to be a useful tool. I am going to talk about this middle thing here, which again is part of the, read section, but I think this really does benefit from an explanation. We have these two different ways to describe curves. We've got these things called parameterizations, and we also have, of course, going way back, y'all know what equations are. And I just want to point out that even though both of them have an equal sign in them, technically they're both equations, right? That's really a pretty superficial take. How these two constructions relate to the curve, very, very different. Parameterization spits points out. It generates points. You give me a value of t, we plug in, and we produce as output a point on the curve. That's not what equations do. I mean, it's really not what equations do not produce points. Equations test points, right? You give me a point on the curve, and then we test it. Right? You give me a point, you say it's on the curve, okay, well, the equation better work. If you give me a point and the equation doesn't work, well, that's not a point on the curve. So whatever point you give me, we can test by plugging in and seeing if the equation works. So notice the big difference, right? So again, both of these things involve equal signs. There's they're really, really different in how they relate to the curve. One generates points, one tests points. And this next example, which again, y'all are going to read, uses explicitly these sort of relationships as the strategy for how to find the answer to that question. So give that a read. Notice how we use the parameterization to generate points. Notice how we use the equation to test those generated points. And then the answer falls out. Okay. All right. Okay, now this is something y'all probably have not seen. I think this is worthy of discussion. It's not that much discussion. By the way, let me get ahead of myself here and explain the notation. This little symbol right here, it's a shorthand. It's just somebody made that up because we find ourselves using a certain phrase over and over and over again, and it's nice to be quick about it. This means there is or there exists. It's very standard. Some of y'all may have seen this before, but probably not everyone has seen it before. So anyway, that's what that is. Then there's this little weird-looking symbol right here. Another made-up shorthand. It means such that or so that. So what I have here is this says there exists some value of t such that this point is computed by that formula. Okay, is that cool? Just again, notation. Yes.
Should we be familiar with the notation?
Yeah, that's right. I think that's there's not going to be a ton of these little shorthands that I'm going to show you. So I think it's a small ask. Yeah, totally. Okay. So what are we doing here? What's the big idea here? We've got a parameterization of a line. Here's so line in R3. Here's how you parameterize it. It's just like a line in R2. Point plus parameter times direction vector. It's just like in R2. It's exactly what you would expect. That is a point generator. Can I make a point tester? And now, of course, the natural first thing to think is, well, yeah, write down the equation of the line, right? Surely there's an equation for lines in space. One would think, and kind of know. Again, equations in space make surfaces, generically. Technically, there is an equation of life. It's impractical and fairly useless. But so I'm going to say, for all practical purposes, there is no equation of the line in 3 dimensions. It just doesn't work that way. So, okay, if we can't have an equation, reasonable next question then, can I, in some sense, come up with a point tester? What would be the test? Specifically, if I want to know, is some point, whatever that point might happen to be, is that on the line that's generated, the line that goes through that point and points in that direction, is that point on that line? The test, I guess, would be, well, is there some value of t that then produces that point? It's not a very helpful test, right? Because I don't know how I would figure out what that t is, but that's if all I know how to do is generate points, then the test is there needs to be a value of t that generates the point that I'm interested in. Okay, so it seems pretty useless. Here's where this gets much nicer. I'm going to make the observation that this vector equation is equivalent to these 3 scalar equations. These are just the coordinate equations. Keep in mind, when you have a vector equation, there's actually, you can multiply it out and look at one coordinate at a time. There's actually 3 coordinate equations in there. And in each of those 3 coordinate equations, you can solve for t. Solve for t in each of those 3 coordinate equations, you get this. Okay, now let's ask, rephrase of our point test. Does there exist some value of t that makes all three of these equations work? And I claim this is a pretty simple question. If there is a single value of t that's equal to all three of these things, I mean, it kind of sounds nonsensical. How could one number equal to multiple numbers? Right? Can you think of a value of t that's equal to 4 and 7 and 19? No, of course not. Okay. The only way that you could possibly have a value of t that's equal to three things is if those three things are equal to each other. Can you think of a value of t that's equal to 4 and 4 and 4? Yes. The answer is 4. Right? Does that make sense? It's silly, but that's the big idea. So this is the test. And it's as simple as this. This is the point tester. If these three things are all equal to each other, then yes, there is a value of t that's equal to all three of these things. And then yes, there is a value of t that generates that point. And if any of these are different from any of the others, then there's no way t could be equal to all three of them. And that means there is no value of t that generates that point. So lovely little observation, cute little bit of algebra to do it. And by the way, this resulting collection of equations is called the symmetric equations. This is terminology. Everybody buying it? Okay. All right. Moving along. By the way, we just finished section 1.2, and this being our my last class of the day, and I did finish 1.2 and 1.3. Excuse me. Finished 1.2 and 1.3 in my earlier sections. We are now officially done with 1.2 in all sections. That will be part of the homework due Sunday. Hopefully we'll finish 1.3 also. I'm pretty optimistic. I think we've got enough time. But we'll see. Yes?
You said that 1.1 and 1.2 are for the homework.
Yeah, and that's right. And you're going to see that on the class schedule once I get back to my office and have time to update it. Yeah, absolutely. Yeah. Okay, so dot products. A lot of this is review. Y'all have seen dot products before, right? Standard construction from linear algebra. Bunch of properties. Y'all have seen all the properties before, I feel sure. Make sure to remind yourself, look through all that stuff. And, for whatever it's worth, it's the model for the idea of inner products. Y'all remember inner products from linear algebra? Really important stuff. Powerful idea. You know how if you have an orthonormal basis, y'all remember orthonormal bases, right? If you have an orthonormal basis and you want to write some vector as a linear combination of those orthonormal basis vectors, orthonormal bases are great because you can compute the corresponding coefficients with dot products. Well, likewise for inner product spaces with inner products. And if you pick the right basis and the right inner product space and the right inner products, you get Fourier series. Fourier series is arguably depending on how you choose to look at it, kind of a rip-off of dot products. By the way, here's another one that you get. If you pick the right vector space, the right inner product to attach to that vector space, therefore the right inner product space, and the right orthonormal basis. And this is the really tricky part, the part that no one figured out until about 40 years ago. You get something called wavelet breakdowns, wavelet transformations. And that's one of the central ideas that makes image compression work. Isn't that wild? Ultimately, kind of a rip-off of dot products, depending on how you look at it. I think that's really cool. Okay. Oh, side note, just for fun, because we're at Duke. the person most responsible for taking wavelet analysis and making it practical and making it powerful, Professor Ingrid Dobeshe's a Duke professor. So, very cool. Okay, moving along. I have a little stump speech that I always feel obligated to give about these two words, perpendicular and orthogonal. A lot of people use these terms interchangeably. I think it's a mistake. It's a missed opportunity at a minimum, right? So let me explain what I'm talking about. There are two ideas that very commonly are simultaneous, but that are not always, that are importantly different ideas. One of them is an algebraic idea, that of two vectors having a dot product being 0. Notice that's purely algebraic. It's just algebra. There's no geometry in what's written down here. Dot product, algebra. Equals 0, algebra. And then there's a geometric idea, and you know where I'm going with this. The geometric idea is that if you have a couple of vectors and you look at the directions that those vectors point, and then you think about, well, what is the angle between those two directions? And you can ask, is that angle a right angle or not? Right? And notice that is all geometric. Directions and angles, all geometry. Here's the problem. That geometric idea only makes sense if you're talking about non-zero vectors. They've got to be non-zero vectors. If you want to talk about, right angles, but one of the vectors is the zero vector, the zero vector doesn't define a direction. There is no direction. I don't know what angle you mean. There is no angle because there is no direction for one of the vectors. The whole thing crashes and burns. It doesn't make sense to talk about, does the zero vector make a right angle with some other vector? It's all nonsense. Does that make sense? Is everybody with me? Okay, so I think these are two really, really importantly different ideas. And when you have importantly different, fundamentally different ideas, well, we should not blur the distinction. And I feel like we should choose one word to use for one and the other word to use for the other. And so perpendicular is a reference to the idea of the directions making a right angle. It's a fundamentally geometric idea. It only makes sense for both vectors being non-zero. And then we're going to use the word orthogonal to talk about this algebraic idea of the dot product being 0. So two different words, two different definitions. Let's not be sloppy and conflate them. Does that make sense to everybody? This, as I like to say it, I wasn't brought up right on this point. I was probably in my early 30s before I decided, hey, wait a minute, what am I doing? This is embarrassingly sloppy, right? So I had 15 years of developing bad habits on this distinction. So I'm hoping that I can catch y'all with only maybe a year or less, possibly, of bad habit to overcome, and maybe you can overcome it more quickly than I did. I'm still kind of struggling with it. You're still going to catch me sometimes saying perpendicular when I meant orthogonal or vice versa. All right, and I'll do my best, but again, I wasn't brought up right. Okay, questions? Is everybody okay with that? All right. Okay, so a couple of things, and again, I'm going to be brief. Y'all can read the details on all this stuff. First, a really quick observation. There's a handy-dandy little formula here for how to make a unit vector that points in the same direction as some given vector v. Easy formula. Not hard to see why it works. Make sure you understand. Make sure you have a good intuition for how this works. Make sure you can prove this. It's not hard algebra. Good exercise. Make sure you can do that. And make sure you remember the formula. Okay. That said, we're going to talk about this idea of a component. the word component addresses a scenario where there is a direction that I want to talk about. There's a direction that is, I'm going to say, the direction we care about. We don't really care what's happening in other directions. It's only the direction we care about that matters. An easy example, football. You don't have to know a lot about football for this metaphor, but if the ball starts here and then the ball is, the carrier is tackled there, well, that's how far the ball moved, but you don't get credit for running sideways, right? You got to run downfield, pass or whatever. So all we actually care about is that. So in order to figure out what that is, how far is this? Well, I'm going to need to know what is the vector in question. I'm also going to need to know the direction in question. The direction is usually characterized by some vector pointing in that direction. And then we're going to have to do some geometry and figure out how to compute that formula. But does everybody understand the picture? Okay. By the way, keep in mind, sometimes you're sacked for a loss, right? The component can be negative. The component should be able to be negative, right? A loss of 10 yards is not the same as a gain of 10 yards, right? Okay. All right. Okay, so here's where I'm going to let y'all do some reading. A little bit of algebra to check up on, no big deal. But the trig of that triangle gives you that. And then y'all can play around with a little algebra. Perfectly readable, good little exercise. Think through, make sure you follow all that algebra. And the punchline is the component, namely that scalar, is computed by that formula right there. All right. Another good formula to make sure you know. And more importantly, make sure you understand what the idea is that this formula computes for us. Okay, now I have a preference. I think an even better formula comes from making the clever observation that right there is the unit vector pointing in the relevant direction, right? It leaps off the page at us looking at this answer. It's right there. Right? So I can rewrite this formula for the component as instead of computing the component with this formula, W dot V divided by the magnitude of V, I'm going to point out that I can think of that as just dot product with a unit vector. And I think this is a wonderful way to think about components. Components are dot products with the relevant unit vectors. It rolls off the tongue, if nothing else, very nicely, right? Components are dot products with unit vectors. Easy to remember, right? And further, if you think about it, why are we looking at unit vectors? In what sense does it make sense that I would only be interested in the unit vector? Why don't I care about V? Why does V not even seem to show up in this formula? Well, let's go back to the picture here. Why should V show up in the picture? V was just a tool. V was just a tool for helping me understand what the relevant direction is. There's lots of different V's that could do that job just as well. Any of these vectors, they all point in the same direction. The direction's all that really is relevant to figuring out the component. So the specific V among these many choices, the specific V that you choose, who cares? Kind of really makes sense that only the unit vector should matter. Does that appeal? Kind of? Okay. All right. Okay. Oh, if I can get this to cooperate again. There we go. Okay. Let's see here. Now, here's a related idea. In fact, it looks really, really related. You'll even notice that picture is copy paste from the previous page. It's the exact same picture, at least parts of it, exact same picture. And here we're talking about, though, a different idea. That's the idea of a projection. Projection is not the same as a component. A component is a scalar. Let's go back up to here. A component is your yardage gain or loss, right? You either gained 7 yards or maybe you lose 3 yards. It's a scalar. That's not what a projection is. A projection is a vector. It's literally the vector that is what you might call the relevant part of W. Everybody see the difference, right? Vectors and scalars are different things. Okay, so we've got a formula for components. How are we going to find a formula for projections? The answer is actually really nice. The projection, being a vector, all I need to know is the direction and the magnitude. The direction is the unit vector, which we already have a formula for. And the magnitude, well, I'm abusing this term a little. Magnitude, again, is an intrinsically positive thing. Let's let that slide for a second. So sloppy. The magnitude is the component, which again we have a handy dandy formula for. Okay, now let's address the sloppiness. What if it's going the other way, right? Well, if it's going the other way, then the component will be negative, and that will literally make the vector point the other way as it should. So even though, it's convenient to talk about magnitude and distance in a case like this, in fact, it's the scalarness, the plus or minusness is the natural fit for what makes sense here. So component times direction is all it is. So this is my favorite formula for projections. This right here. I like it because it makes sense. I will never forget this formula in a million years because I understand the underlying ideas behind it. It's a direction and a magnitude, and the direction is obviously, what else would it's got to be the unit vector, and the magnitude, the picture, it's the component, and we already know how to compute components. So instantaneous. Okay. Now, the book proposes this alternative formula is also perfectly fine. This alternative formula has an appeal to it because it's explicitly in terms of V and W. You give me a V and a W, boom, plug and chug, right? Brain off, computation on, right? You can just do it. And again, that has an appeal. All of us in our upbringings were probably somewhat encouraged to think that way. Again, I think that's a mistake. And I started to overcome this mistake around the same age that y'all are right now. So anyway, try not to fall for the allure of the fact that this is plug and chug ready. It's the wrong question. It's the right answer to the wrong question. The question isn't, what can I plug and chug with? The question is, which of these two formulas fits better with understanding and ideas? And I propose this one makes loads of sense. I can read this formula straight off the picture. It's conceptually natural. This formula, I can prove it and stuff, but there's a couple of steps there, and why is it? Oh God, is it V dot V or is it W dot W? Oh, how do I remember? And you can see it's not particularly natural, really. So I consider this formula to be a distraction, a little bit of a distraction. You can memorize it if you want for streamlining your computations. I think this is the much better way to think about this idea. All right. Okay, and I think that will basically, y'all can read there's a couple of plane geometry proofs that you can do with vector out. It's kind of cool. Take a look, but that's, again, very easily read. So we are now done with 1.3. So that is almost certainly, that's guaranteed, in fact, to be the end of the homework assignment, is because there's no way we're going to finish 1.4. Yeah?
So projections are vectors or scalars?
Yes. Projections are vectors, components are scalars. Yeah. And that, you just have to remember which way it goes. Yeah, right. Unfortunately, not all books use these terms exactly in the same way. So heads up, depending on the textbook that you're looking at, in some future engineering class or whatever, if they say projection and they write down the formula for component, okay, whatever. Definitions are annoying, right? And don't sweat it. But in this class, we have to make that distinction. Yeah. Okay, we've got 4 minutes. Let's make a little bit of headway on 1.4. Cross products. Most of y'all have probably seen cross product in some sense. If not, don't worry about it. Cross products connect really naturally to determinants. I feel sure y'all have all seen determinants. Really cool connections between cross products and determinants. We'll talk about that next time. And they also relate to what I'm going to call the geometric order of a list. I think this is underappreciated. I think this is particularly nice math. So this is what we're going to start with. We should be able to do this in the next couple of minutes. When you have a list, not a set, A and B are not just a couple of vectors that you threw into a bag. Right? This is a ordered list. One of them is first, one of them is second. Right? The order matters. You have a list of 2 vectors in R2. That first vector, perhaps, might be like so. The second vector might be like so. Notice that with A first and B second, it's like I start with that direction, and then I end with this direction, right? A first, B second. And thinking of that progression, I'm kind of going counterclockwise. So I'm going to call that a counterclockwise list. Does that make sense? Okay, so I would call that list counterclockwise. Now, on the other hand, the first vector could be perhaps like that. The second vector could perhaps be something like that. If that's what the vectors A and B are, same list, now A first, B second, clockwise. So this is kind of a, every list you would, most lists you would expect to be either clockwise or counterclockwise, and you just look at the vectors and see which way you rotate to get from the first one to the second one. Now, annoyingly, sometimes the first vector and the second vector are parallel. And then it's kind of, it's sort of neither, you know what I mean? The vectors might point in opposite directions. Again, kind of neither. One of the vectors could be the 0 vector. Okay, well then again, kind of neither. Right? So various different versions of neither. What you're going to notice when you think about all the different ways that clockwise, counterclockwise might fail, they all make for a list that is linearly dependent. In fact, they're exactly the different cases of linear dependence. So this is the complete list of possibilities. When you have lists of 2 vectors in R2, it's always either counterclockwise, clockwise, or linearly dependent. And this is something that's mathematically natural. Counterclockwise is a reflection of clockwise. Right? If you switch the vectors, if you take the first one, make it second, take the second one, put it first, the list changes order. A to B is counterclockwise, B to A, clockwise. And then lastly, you can rotate the picture all you like. So, for example, let's look at my watch here. And my watch, the hands go clockwise, right? The better. Clockwise. What? Now I'm rotating everything. Yeah, they're still going clockwise, right? So rotations don't affect a list. If you have a list and they're counterclockwise, if you rotate everything, it's still counterclockwise. Okay. All right. So we're going to actually see how this is mathematically significant. It has a direct connection to determinants. We'll fill in those blanks and take it from there on Friday. Y'all have a good rest of your day. See you later. Okay. Give me a second to wrap this up.